Okay, there are quite a few different types of rational functions that we can graph. So I'm going to start with a particular type when there's no variable in the numerator. So my numerator here is just a number, right? So this method's going to apply when I've got just a number for the numerator, okay? So we can start by making an XY table to graph some points. And we'll just plug in some xy values, okay? So when I plug in 0 for x, I'll have 1 divided by 0. Well, that's going to be undefined, okay? When I plug in 1/2 for x, let's think about that. I'm going to have, I'll just write it right here, y over 1/2, 1 over 1/2. So that's 1 divided by 1/2. That's the same as 1 times 2, right? I can flip that fraction around to make multiplication, and then, hey, this equals 2. Okay? 1 divided by 1 is 1. 1 divided by 2 is 1/2, so I'll just put 0.5. Okay? If I'm divided by -1 or positive 1/2, I get 2. So when I divide by -1/2, I'm going to get -2. 1 divided by -1 is -1. And then 1 divided by -2 would be -0.5. Okay, so then I've got some x, y values. Okay, so let's plot those on this graph here. I got 1/2, 2 right there, 1, 1, 2.5, and then I've got -1/2, so half to the left, 2 down, 1 left, 1 down, and 2 left, 1/2 down. Okay, so once we get used to these patterns, we won't have to make an XY table, but it's a nice way to get an idea of what this is going to look like. And you can always use that method in an emergency. Get some points, and then you have an idea of what the graph looks like. Okay, now the one I didn't graph was 0 undefined because I can't really graph that. So when x equals 0, well, let's think of all the points where x equals 0. There's 0, 0. 0, 1, 0, 2, 0, 3, 0, -1, 0, -2. All of these are undefined, okay? So what's going to end up happening is I'm going to have an asymptote right here on the y-axis. So this is going to be a horizontal asymptote. Oh, sorry, a vertical asymptote. Okay, and it's the y-axis. You could just say it's the y-axis, but the equation of that line would be x equals 0, because those are all the points where x equals 0. Okay, it's a little bit harder to see on this one, but there's also going to be a vertical asymptote. So let me try to explain this with the x and y intercepts. Okay, so I already know there's not really going to be a y-intercept. I'll get back to that in a second, but let's try finding an x-intercept. I'm going to plug in 0 for y. Okay, and then I'm going to solve this for x. Now, 1 divided by what would equal 0? That would have to be 0, right? 1 divided by 0 is 0. So x is going to equal 0. So, sorry, what am I talking about? You can't divide by 0. Just kidding. That was a trick. And no, it's just early in the morning and I was forgetting that you can't have a 0 in the denominator, right? So I can't divide 1 by anything and get 0. Even if I divide it into a million parts, there'll still be a little bit left, right? If I take $1 and cut it up into a million pieces, there'll still be a millionth of a dollar, right, in each pile. So you can't divide and get 0 as an answer, okay? So another way to think about this, I could multiply both sides by x. And then I have 0 times x equals 1. Well, there's not going to be anything that works here. This is undefined, okay? And algebraically, the y-intercept's also going to be undefined. So because I'm going to plug in a 0 for x, and I get a 0 denominator there, so y is also undefined. Okay? So, all right, so I've got that. This kind of represents the undefined x values, but there's also undefined y values. So there's going to be a second asymptote. This one's going to be horizontal. So this is going to have a horizontal and a vertical asymptote. My horizontal asymptote is the x-axis, also known as the line y equals 0. Okay? So maybe you can see what's going to happen. I'm going to get some curves that are going to fit in with the asymptotes that I already drew. So I'm going to get a curve that looks something like this. Okay? So the key to graphing these types of problems is finding the asymptotes. I call these crosshair problems. I've got these crosshairs. If I can figure out where the crosshairs go, then I can make a pretty decent sketch of this just by sketching in some lines that hug the corners. Okay. Now, so with these ones, you're always going to end up with the curves in opposite corners. Okay. So typically they would be in the bottom left corner and the top right corner, but if we've got a negative value, then it's going to switch, okay? So this is going to have the same asymptotes. If I try to do the x and y intercepts, the same, they're going to be undefined, just like on the last example. So I'm going to get asymptotes on the axes again, okay? So for 1 over x, it's in these two corners, but when you have a negative fraction, it's going to switch into these two corners, okay? And I'm not going to graph the points, but I'm just going to do this kind of thing just to make this kind of quick. It's going to go something like that. And I could always get some xy pairs to get a little bit more accurate with my graph. But in a nutshell, yeah, that negative is going to switch to these two corners for the curves, okay? All right, let's take a look at the next page. Okay, next page. Got this example. Hey, this is a quadratic equation, and this would be a parabola if I graphed it. And we're not going to be graphing parabolas in this section or in this chapter. But if you know how to find the vertex, that's going to be useful because it's kind of the same way that we're going to find the center of the crosshairs. Okay. So the vertex here, I take this and set it equal to 0. So x would equal 2, and then this is the y value. So the vertex would be 2, 1. It would open upwards from 2, 1, that particular parabola. But that's just asking me for the vertex, okay? And then you can see this has some things in common with that, right? But this is a rational function instead. So I've still got just a number as my numerator. There's no variables in the numerator. So this is gonna be a crosshair type problem. First thing I want to do is find the center of the crosshair. I'm going to do that same way as I did before. So it's going to be the point 2, 1. So I take the denominator, set it equal to 0, and that means x would equal 2. And then, hey, this is my y value, y equals 1. So my center is going to be the point 2, 1. Okay? So I'm going to go ahead and plot that because part E, even though I haven't gotten there yet, is going to be to graph. So I'm going to kind of graph this as I go. So that is the center of the crosshairs. So I'm just going to put a little dot there, and that's where my two asymptotes are going to meet. So I'm going to have a vertical asymptote and a horizontal asymptote that meet right there, and I can sketch those in right away. And if I was ever asked for the equation of these, I could give that, right? This would be the line x equals 2, and this would be y equals 1. It didn't ask me to do this, but why not? There's my asymptotes, okay? They meet at the point 2, 1, right? Okay, oh, it does ask me to do that. Wow, okay, it is early here. So, it's given away by where this meets, right? So, just think of the coordinates there, x equals 2, and y equals 1. Those are the two asymptotes, right? And then, you might need to know which one's horizontal and which one's vertical, but if you've got a graph in front of you, it's pretty obvious. So this is my vertical asymptote, and this one would be my horizontal one. Okay. All right, let's find the x-intercept. Okay, well, I'm going to plug in 0 for y to find the x-intercept just like I would in any equation. Okay, and let's see if we can solve this for x. So the first thing I'm going to do is subtract 1 from both sides. Okay, and now I want to solve this for x, so I want to get the x out from under the fraction. I want to get rid of my fraction. So you could multiply both sides of this equation by the quantity x minus 2 by this, and then you'd get x minus 2 times negative 1 would equal 1, right? And nothing wrong with that, but you can also use this maneuver that I've invented. I'll let you use it for free. I'm hoping to get rich off it someday. I call this the incredible switch. I might have shown you this before. But when you have something that's equal to a fraction, you can just take the denominator and switch it with the -1. And where you're going to end up algebraically, if you clear the fractions and then solve for x, those are going to switch places. And that's why I call it the incredible switch, because there's an incredible switch there. They just swapped positions, okay? And now working on this, x minus 2 is going to equal -1. That's just -1. Just add 2 to both sides. Okay, and this is going to be useful because for two reasons. It's going to give me a point on the graph, which is great. That's always a good thing. But this is also going to kind of confirm where my graph is going to go. So x equals 1. That's my x-intercept right here. Okay, and then I'm going to find the y-intercept. Okay, so plugging in 0 for x. So this one I don't have to do any incredible switch or anything. I just start simplifying. I've got -1/2 plus 1. So that's going to be +1/2, right? Okay, so that kind of confirms, oh, I'm going to have a curve down here, and then I should have the mirror image of it up here. And it's going to be in these two corners because this fraction is positive, right? If the fraction were negative, then it'd be in these two corners, but it should be in these two, okay? And you could start plugging in some more x values if you wanted to keep working on this, but eventually what you're going to see is you're going to have a curve like that, and yeah, it's going to be reflected. Same kind of thing happening over here, okay? And if you have different numbers as your numerator, all that's going to do is change how close the curves are to the asymptotes, how closely the curves are hugging the asymptotes. It could get a little bit looser sometimes, or be closer into the asymptotes as well. But there we go. Okay. Okay. All right. Rational functions with holes. I've got a whole second kind of rational function here. A rational function with a hole always is going to have a variable in the numerator. Okay, so I can see this problem's different than my crosshair ones because it's not just a number up top. There's a variable up there. Okay, so what I want to do first with these is do any factoring that I can. So I can see the bottom I can't factor, the denominator I can't factor, but I can factor the top of this because it's a difference of squares, right? X times x equals x squared, 3 times 3 equals 9. It's a difference. So, you know, this x would be my a, and b would be my, 3 would be my b, and it's going to be x plus 3, x minus 3 when I factor that. Hopefully you remember that because that's going to be very important on problems like this. And now when I'm looking at this, I'm thinking, okay, I can cancel. I can do some canceling. So we can cancel factors, right, when you have a fact, because x minus 3 over x minus 3 equals 1. So then I've got just x plus 3. All right? So now when I boil down this equation, I was just simplifying this fraction part, but this all really equals just y equals x plus 3, right? So, hey, that's just a line, okay? But wait a second. Let's go back to the original equation and think, what would my domain be? Okay, remember we can't have 0 as a denominator, which I was forgetting at the beginning of the section. But yeah, we can't have that whole quantity equal 0. So I know x minus 3 can't equal 0. So that means if I solve this for x, x can't equal positive 3. If you plug it in a positive 3, then we've got a problem there. We got a 0 in the denominator. Okay, so when this says identify any holes, this is a straight line, except there's one issue. I'm going to have a hole at x equals 3. Okay, or you could just say x can't equal 3. That means the same thing. Okay, so I'm going to graph the line y equals x plus 3. So remember, this is my y-intercept here at 3. And then I've got a slope of 1, right? This is in slope-intercept form, so I go up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. I'm doing this kind of lightly, okay? But this is what the line would look like, okay? But I want to think, okay, wait a second. X cannot equal 3. So I'm thinking, okay, well, here's the point 30, the point 31, 32. These are out of bounds. So this is kind of like an asymptote on this problem, except it's not going to be a curve that's kind of hugging that line. But those are outlawed values, right? X cannot equal 3 for this particular problem. So I'm going to graph this line, but I'm going to put a gap right there when x equals 3, okay? And then I just draw in the rest of the line. And don't stop right there because it can continue on the other side of that hole, okay? So it's the line y equals x plus 3, except it's missing the point, what would be, this would be the point 3, 6, right? 3, 6 would be on the line y equals x plus 3, but it's not in this rational equation because when we simplified it, we canceled out that denominator, but in the original equation, that would give us a 0 denominator there, which is no good. Okay. All right. So it's really just graphing. Once you simplify it, it's like graphing a line, but you got to keep the whole in mind. Okay. All right. Let's try one on the next page. Okay. So trying another one of these. Okay. So I'm looking at this. Oh, it's not a crosshair problem because I got an x in the numerator. So let's start. Hey, this is another difference of squares, right? So that's the top's going to factor into x plus 2 times x minus 2. And then I'm thinking, oh, I can reduce. By the way, I can't just cancel out one of the x's here because you'd have to be able to factor out those x's, right? You can only cancel factors. You can't cancel terms, or you can't reduce the 4 and the 2. Because you'd have to be able to, they'd have to be factors. But now that I've factored this, I can do that. Okay, so this is going to have a lot in common with the line y equals x minus 2. Okay, except I got to think, well, what did my original denominator say? Because I've got an undefined x value there. X plus 2 cannot equal 0, so that means x can't equal -2. Okay, so it says identify any holes. I'm going to say x can't equal -2. Or you could say you have a hole at x equals -2. That means the same thing. Okay, and I don't care if you draw in the asymptote, but if it's helpful, x equals -2. Here's all my -2 values for x, right? So that's going to be where the undefined x values are. So then I'm just going to graph this line, but I'm going to make sure when I hit this dashed line, I'm going to make a hole, okay? All right, so looking at this, y equals mx plus b. So my y-intercept is -2. My slope is 1, so I'm going to go up 1 to the right 1, or I could go down 1 to the left 1, down 1 to the left 1. But wait a sec, I'm on that dashed line there, and make sure you don't just stop there. Down 1 to the left 1, and there we go, okay? And I want to point out also that it's not always going to factor nicely like this and reduce like this. This is just a particular type. So there are other rational functions that we're going to be graphing where it just doesn't factor and reduce like this. Okay, but that's going to be a different story. These types will just be a line with a hole in it. Okay, that's it for this time, and I'll see you next time.